Thank you.
Yeah, that one.
Okay.
Can I introduce?
Yes, yeah. Okay.
Hi, everyone. It's our great pleasure to have Subir with us today for our forum seminar. Subir really is the kind of person that needs no introduction. So I will just briefly say that he has made seminal contributions to theoretical condensed matter. Is one of the leading condensed matter theorists of our times. And today, Subir is going to tell us about cuprate superconductors. Subir, you have the stage.
Okay, thank you, Dimitru, for the kind invitation to be here. It's a pleasure to be back at Oxford, although my first time giving a seminar in this building. And thank you for the kind introduction. So yes, this is about the cuprate superconductors, which perhaps you've heard a lot about. They were discovered, I don't know, nearly 40 years ago now. And there have been talks about many other superconductors since then. But really, this is still the champion of superconductors. It's the only superconductor that you can make a big pellet of and hold in your hand and dip it in liquid nitrogen and see superconductivity. Recently, there's been a lot of excitement in using YBCO. These are wires of YBCO over here as powerful magnets for fusion energy. There are many companies around the world, including in the UK, that are making these things. And so that gives us more motivation to try to understand these materials better. Okay. All right, so the basic structure of the material is rather complicated, but fortunately, it turns out we only need to think about, for most of the discussion, a single layer of copper atoms that form a square lattice. So these are the copper atoms over here. And at a certain composition, this material is an insulator. And so there's, in fact, only one electron per copper that's active. These are the blue arrows showing the spins on the copper orbital. And they have an antiferromagnetic exchange coupling between them. And it turns out that the ground state is this antiferromagnet, where half the spins are up and the other half are down. Okay, so that's the parent state we have to work with. And when we change the density of electron, this is what forms a high temperature superconductor. So there was a brilliant and important paper by Bill Anderson in 1987, where he said, in fact, this was before it was really known that the copper spins form an antiferromagnet, that really the relevant state we should think about here is what we call a resonating valence bond. And so this state pictured here, where the spins form singlets, which are eigenstates of the exchange interaction between nearest neighbors. But then, because there's an exponentially large number of such singlets possible, different possible dimer coverings of the square lattice, he postulated a state, which was actually postulated earlier by Linus Pauling in a different context, which would explain cuprate superconductivity. Okay, so that was a claim made at a time when there really wasn't any theory of such resonating valence bond states. And now 30 plus years later, we do have a well-developed theory of such states. We know these states have, in some fundamental sense, long-range quantum entanglement that no other states before then, except, of course, the fractional quantum Hall state had. And for states with a gap, there is very powerful mathematics, complicated things called unitary modular tensor categories that classify such states. So I'm not going to go into any of that. But that's what's taken so long. Just to understand, even for an insulator, the different types of states possible has required development of a lot of new physics, which so far I would say main application has been other fields of physics like quantum information or quantum error correction. But one feature of this state is that it has long-range entanglement, but it's really entanglement of bosons, because the only thing that's entangling are the spins of the electrons. So if you think of a down spin as a boson, those bosons are moving around, and entangling with each other. So you would say that today we have a very solid understanding of many boson entanglement. But what's missing is many fermion entanglement. And so today I'm going to tell you about some of our work on how we entangle fermions that move around and how it relates to some of the observations on these materials. So what is the basic underlying property of this state that's novel? Well, one way to say it is that this is a state that has excitations which are particle-like, but they cannot be created by local operators. So imagine you have a local operator which takes a singlet and converts it into a triplet. And now what can happen is that these two spinor halves can separate from each other. And so one of them can run off to infinity. And now you're left with a local excitation, which is this spinor half here, which when it's moving around has now some strange quantum numbers. It has spinor half, but no charge. So this is what we call a spin-on. And then, no spin-on had ever been discussed in any previous work. In any of your textbooks or Landau-Lifshitz, you will never find such an excitation, which carries half into the spin and no charge. And so that's the basic property of these states. So you cannot create the spin-on. It's the physical object that exists in such states, but it cannot be created by a local operator. And what we learned since then is that gauge theory is the natural way to talk about these things. And so each of these objects carry a gauge charge under some gauge group. And you can think of the second spin-on running off to infinity as the Wilson line of the emergent gauge field that's tied to it. And that's how you can then develop theories, of which we have many now, of such states of matter. Okay, so I won't say much more about that. All right, so here's the actual cuprate phase diagram, where what we have done is removed the density P of electrons from the square lattice. So this is the axis P. And for P around 0.2 is where you get very high temperature superconductivity. Okay, now there's one very important thing I want to emphasize, be central to my discussion, which is, we say there's P holes. But really, if I was a semiconductor physicist, I would not say the system has P holes. Because semiconductor physicists always measure holes or electrons relative to a filled band. So if you have a filled band and you remove P holes, which is what you do in silicon, then you have density P holes. So in this case, a filled band has 2 electrons per site. And so relative to the fully filled band, the density of holes is actually 1 plus P. And similarly, if I want to think in terms of electrons, well, you can just see there's exactly 1 minus P electrons. So the density of electrons is 1 minus P. And that's really, if I was doing anything in Fermi liquid theory or anything based upon Landau-Lifshitz, I would say the density of holes, at least in a system that's not an antiferromagnet, is 1 plus P, and the density of electrons is 1 minus P. Okay, and the difference between 1 plus P and P will be the main important thing in my talk, so please be clear about it. Okay, so now if you measure the system in this region, so-called Fermi liquid region, where conventional theories sort of apply, and you measure the Hall coefficient, which is the way you measure density of holes in a semiconductor, you get a density 1 plus P. Okay, so why is it 1 plus P as holes and why not 1 minus P electrons? That has to do with the shape of the Fermi surface. So this is photo emission data on the Fermi surface. These are the occupied states. There's just a single band, so it's a very simple system. And these are the empty states. And it's the empty states that form a closed pocket-like surface, which is approximately circular. And that's why you can think of this as 1 plus P holes. Okay, so that's a little deep, that works beautifully with conventional solid-state physics. So here, everything is in good shape. Furthermore, there's another very important theorem, which will again be central to everything I'm going to talk about, which was proven already by Luttinger in 1960. But since then, we have realized that this is a deep theorem which has a topological character. So it's a piece of 21st century physics that was already discovered in 1960. So what Luttinger proved was that electron interactions don't change the area enclosed by the Fermi surface for states that are smoothly connected to the free fermion state. So the area enclosed here does not depend on the strength of the interaction between the electrons. That can change the shape. Certainly, interaction can change the shape of the Fermi surface, but they can change the area it encloses. So here again, you can just see the Fermi surface in photo emission. You can measure this area, and beautifully it works as area 1 plus P. All right, so even Luttinger is in good shape, and that's an exact result that has to be obeyed by this system. Okay, so now everything is in great shape, but now let's of course go to the interesting region at smaller p. Well, then you see Hall coefficient of p, not 1 plus p, holes of density p in many observations. So that would be fine if you were in this region here, where you do have antiferromagnetism. If you do have antiferromagnetism, the picture I showed you with p holes and an antiferromagnet perfectly applies. But you see this not just there, but in this entire so-called pseudo-gap region, where there is clearly no antiferromagnetism, but nevertheless, you see density p holes. And that, in a way, is the central problem of the field that many of us have been grappling with for a long time. And there are many theories, including some by me, of saying that, well, okay, fine, there's no long-range order, but maybe there's fluctuating order. That there's, you just look at the system, there's all kinds of ordered state at low temperature, not only antiferromagnetism, but superconductivity, and under certain conditions, even charge density waves. And okay, so you do some very complicated theory of all these fluctuating order parameters, and maybe that'll explain the pseudogap. Okay, so I would say that has been the dominant point of view in the field. And it's fine, it has had quite a few successes. But it's, it's very difficult to work with, but anyway, okay. So today I'm going to talk about a very different point of view, and also talk about some new recent experiments just in the last year, which I believe are incompatible with this point of view. So the point of view will be that this pseudo-gap region is not some conventional phase of fluctuating orders. After all, it's appearing at relatively low temperatures. 200 Kelvin is very small compared to the exchange coupling, which is almost 2000 Kelvin. So it's really very low temperatures. And so I'm going to argue that this is really a quantum phase. It's a novel quantum phase where you have to think about it in its own terms, not as fluctuating of something else. So we have to classify and understand it. We have to think about quantum phases of mobile fermions with long-range entanglement. What are their properties? And do they agree with some observations on this region? So in contrast to all the intensive work on bosonic quantum entanglement, and every quantum computer you have today is bosons, except for a few exceptions. They don't call them some quantum computers. There are works in optical lattices where they're actually fermions moving around. And in fact, I'll discuss some of that work soon. But everything by Google, everything by Quantonium is boson. So they aim to understand this region, at least they say in their publicity, by putting lots of Jordan-Wigner strains. Okay, fine, but I'm not optimistic that that is going to work out. Anyway, sorry for that. Snide remark. Okay.
So if one goes across at, I don't know, 150 or something.
Yeah.
How does the coefficient interpolate between one value and the other?
Okay, that's an excellent question. In fact, Nigel Hasse and I were just discussing that on Monday.
Yeah.
But let me not go into that. I want to talk about the two limits. The short answer is we don't understand what's happening as we go across. So I just want to talk about, I already talked about this region where, let's say everything is understood. Now I'm going to stick here. I'll say a few things at higher temperatures of what happens in between towards the end. All right. Okay, so what I'll talk about two examples of entangled phases of mobile fermions. One is which we call the fractionalized Fermi liquid, which I'll argue applies to the pseudogap regime. And one way to think about it is sort of a coexistence between the two phases that we now understand very well. When you have mobile fermions, we know they form a Fermi liquid with a Fermi surface. And when we have bosons, we know they form spin liquids. So this phase has both the characteristic. It's like a superposition, crudely speaking, of a phase of matter which both has the spin-ons of a somewhat bosonic spin liquid and mobile fermions with the Fermi surface. So this is what we call FL star. The FL meaning Fermi liquid, the star meaning it's fractionalized. Okay. You can blame Senthil for that notation, but okay.
You were assistant advisor, so we would blame you.
This was done after he was my student.
Can I use this?
Future? That was a bad one.
Okay, so that's one class of, fermionic phases, which is not quite fermionic because the entanglement kind of is inherited from a boson. But for the strange metal, and this I'll hopefully say a few words towards the end, you're really an intrinsically fermion liquid. And I've somewhat presumptuously called it an SYK liquid. So this is a state of matter which is intrinsically fermionic and has no quasi-particles at all. No anyons, no boson, no fermions in its spectrum. And the SYK model is a zero-dimensional model for which you can explicitly prove that, compute a lot of these properties for a state without quasi-particles. But of course, that's a zero-dimensional model, and hopefully I'll say a little bit about how you make it more realistic. That's what we've been working on in the past few years by some two-dimensional, what people call the two-dimensional Yukawa SYK model, and how it can capture some properties of the strange metal. Somewhat unexpectedly, the original SYK model, which is a zero-dimensional model, has turned out to be just the ticket to make real progress on the low-energy theory of generic charged black holes in asymptotically flat three-dimensional space, I mean R space. So any black hole which has a net charge, then at very low temperatures, we now know what the density of space looks like. But I won't talk about that here for lack of time. But let me just say the answer is very different from what string theory told us, which considered only supersymmetric black holes that have supersymmetry even at low energy. All right. Okay, so what is this FL star? So most of my talk will be about the first type of entangled fermion state. So I'll just make a few pictures. First, let me define what it is, and then I'll show you in pictures what its wave function look like. So first of all, a Fermi liquid, as I've already said, take a system of holes of density rho. You have a Hall coefficient of density rho, and the area enclosed by the Fermi surface, as Lerdinger taught us, is rho over 2. This is in units where the area of the Brillouin zone is 1, and the 2 has to do with spin. These are very convenient units to work in. You can forget all these 2 pi squares that float around in any Lerdinger argument. You just count states. And so there's 2 states per momentum point. The density is rho, and so the area is rho over 2. Okay. So now I mentioned earlier that the Lerdinger result is from 1960 using pages and pages of Green's functions that I could never understand in graduate school, but I was very impressed by them. But today I'm even more impressed by a much better argument by Oshikawa in 2000, which is just a few pages, which everyone should read. It's quite elementary, which established the same result. And in a modern language, it has the spirit of a 't Hooft anomaly, or the Laughlin flux piercing argument. So I'm calling it the Oshikawa anomaly. Purists like Senthil said, no, Oshikawa didn't really have an anomaly. So I changed it to satisfy him as an anomaly argument. Okay. I don't understand. I'm not a purist.
So the anomaly stop.
All right, but it's really, in the end, it's relatively simple. You take your many electron system, whatever it is, similar to what Laughlin initially used to prove the quantization of the Hall effect. But here there's no magnetic field, and there's no gap either. And you take your many fermion system, put it on a torus, and you insert one flux quantum through the whole of the torus. So as you're inserting the flux quantum, by Maxwell's equation, that induces an electric field, which imparts a net momentum to the electrons. So given a Hamiltonian, you can compute the change in momentum of the ground state under flux insertion. Exactly. It's no problem. And in fact, the answer, modulo some factors of pi and h and so on, is just the density. So, all right. So that's the UV, if you wish, the UV argument that tells you exactly, UV meaning the density itself is a local observable, which depends on all energies. So it's really a high energy argument, which tells you what the value of this anomaly is. There's a mixed anomaly between the charge conservation and translation. Okay, so then you make an assumption. You make an assumption that the low energy state of the system is just a Fermi surface with some quasi-particles on the Fermi surface. And for this, so you just take the free quasi-particles on this Fermi surface, and you compute the same anomaly. You look at the effect of that flux on the same quasi-particles. And so that's, again, something you compute, given that assumption. And then you equate these two values, and you get the Luttinger result. So that's a beautiful general argument, and really the correct way to think about what Luttinger established. Another nice thing about Oshikawa's argument, it makes the assumptions under the result very clear. The central assumption is that the only low energy excitations on a torus are the quasi-particles. That's the condition under which this result, Luttinger result, is valid. And so that opened the door for us to say, oh, there's other ways to satisfy Oshikawa. Let's not worry about Luttinger. Oshikawa's result is more powerful. You can violate the Luttinger area. How? Well, you just need a state which has other low energy excitations on a torus. Right, that's all you need. So in particular, you could imagine that there's some spin liquid character of your system, and that can take away density 1. So you could have a state with a Fermi surface enclosing area corresponding to density rho minus 1. And these are the regions that will also give you the Hall coefficient of rho minus 1, which is P. That's what we call a fractional Fermi liquid. And there's no broken symmetry or anything, no order parameter needed. It's just that you have some other excitations around that are needed to satisfy the Oshikawa anomaly. And it's satisfied by the spin liquid contribution 1 and the Fermi surface anomaly, which is the usual one for Fermi surfaces, which is rho minus 1. Okay, and one important thing is, we've learned since then, even at that time, we had understood most of this, that the spin liquid anomaly is quantized. It can't be any number you want. Almost all the spin liquids we've been studying, the so-called odd dimer models, for example, have a quantized density, which is 1. So the anomaly is quantized, which means, so it's nice to have a little flavor of the quantum quantization here. The area of the Fermi surface can be anything. It's always rho minus 1, at least for the most common spin liquids. You can involve some more exotic states, which will subtract by other rational numbers. But that's almost all, most common one we want to think about. All right, so that, if you wish, is a prediction of this analysis without saying anything about how this happens. And if you had 4 pockets, which you do in some of the models I'll discuss, then the air, before I get there. So if you ever measure this, you solve a long-standing challenge. People say, okay, you've got some entangled states. How can I measure the entanglement? This is one of the best ways to measure entanglement. See a Fermi surface that does not have the Luttinger value, because This is essentially rigorous argument saying that there is some entangled state that's satisfying the anomaly. Okay. And if there's 4 pockets, the area of each pocket, if rho is 1 plus p, would be p over 8. Okay, p over 8 will be the central predictions I'm going to talk about. Okay. All right, so now let me show you how, just at least at a pictorial level, using very crude arguments, show you how what does such a state looks like? What does FL star look like? So these arguments are very simple in the end. And so not to imply that the actual cuprates look like this. But the beauty of the Ishikawa anomaly argument is that as far as the area of the Fermi surface is concerned, it's exact. Okay. Many other things are not, but we don't care. We just want to use the simplest picture to get the value. Okay. All right, so suppose you had long-range order in insulator like this, then the Brillouin zone is half to this dash Brillouin zone. Then you put a density P holes. So these will move around, and you can do a simple calculation in the background of this order, and you find you get these green pockets. Now, or valleys, let's call them valleys for the people who work in TBG. The question is, how many valleys do you have? Or in semiconductors, you call them valleys too. Well, there's only 2 valleys because there's this pocket and that pocket, but because the Brillouin zone has halved, this pocket is the same as that pocket. So there's 2 valleys, and these are conventional quasi-particles, so they carry both charge and spin. So there's 2 valleys and 2 spin. Therefore, the area of each pocket is P over 4. Okay, so this will be an area you'd measure in photo emission or in quantum oscillations. And there's beautiful recent experiment by the group of Kondo just a few years ago where this has been done. And yes, you get P over 4, no question, in both experiments. And not a surprise. This is what Landau Lifshitz would tell you too. Okay, but now let's go to some exotic state. So this is the kind of state that was much discussed in the early days, and even more recently, where you have the RBB, the resonating valence bonds around, but you have a few vacancies. So now as the valence bond resonate, the vacancies can also move. And as you notice, as it's moving around, it's carrying charge, but not spin. So this vacancy is not what you'd call a hole, because a hole in semiconductor physics carries both spin and charge. This is what people call a holon. Just to tell you, it's actually an anyon. It's not something you can create by a local operator, and because it carries charge, but no spin. All right, so now one very important feature of this holon that will be key to the experiment I'll show is that this holon cannot tunnel from one layer to the next. It's an anyon that just lives in a given layer. It cannot coherently go from one layer to the other layer because anyons are tied to that entangled state they sit in. Okay, so there's no coherent interlayer transport. Now you can add, so these holons can be bosons or fermions. I would say that if I'm going to use this to describe the cuprates, the bosonic picture doesn't really work because these bosons of density P don't give you a Hall coefficient of value P, but fermions do. So let's imagine they're fermions as they are in some states, some entangled states. Well, then by the Ishikawa anomaly, there must be a Fermi surface. So again, when you do some calculations, you find 4 pockets, but now the Brillouin zone is the full Brillouin zone. And let's say there are 4 pockets, and these are spinless. So you have 4 valleys, but no spin. So again, there's a factor of 4, but for very different reasons. So the area of each pocket is again P over 4, just like in the antiferromagnet. But these are no longer tied to any special point of the Brillouin zone. They don't have to be symmetric about the magnetic Brillouin zone, although unfortunately I've drawn it that way. And the quasi-particles are very different. The quasi-particles carry charge but no spin. But if you're doing quantum oscillations or any transport measurements, you wouldn't know because you're not measuring spin. If you're doing photo emission, you would, but photo emission is very complicated, and I don't want to go into that. Anyway, but the most important difference from the antiferromagnet is this feature that there's no coherent interlayer transport. All right, so finally, so those are the two straw candidates I've set up. So let me go to the candidate I really like. And that's, I'm going to construct in the following way. So imagine I have a hole-on metal, but then I create some excited state where I break some singlets into spin-ons. So each such spin-on will cost me an energy of out of the exchange coupling, which is J. And now imagine these spin-ons move around, and each of them finds a hole-on. And then when you're next to a hole-on, they can resonate with each other and, in fact, gain an energy T, because that's the hopping matrix element. So if T is much bigger than J, roughly speaking, then the energy gained by forming a bound state, by paying the cost of peeling off spin-ons from the ground state, will be recovered. So you will always do this in the ground state. So now I have a different ground state, which is what FL star is here, where you've got, if you think in terms of the dimer picture, I have dimers, which are two different colors. And these dimers can resonate with each other. So if I looked at it in a colorblind way, this is just the same old spin liquid. So the spin liquid, quantized spin liquid, is still there. Nothing has changed about the character of the spin liquid. But if I now turn off my colorblind glasses, I see that some of them are these blue dimers, which carry no charge or no spin relative to the background. These are just the singlets. But the green dimers carry both a charge and a spin, because they've got an empty site for charge +1, and they've got a free spin, which is, so they're spin a half fermions. They have to be fermions because, in fact, they're basically electrons. So I've gone through a lot of trouble to create anyons and then get rid of them. But not really, because I've got the number of fermions I've got back is not 1 plus P, which is what I would have had in the Fermi liquid picture, but P. I've lost one of them. And that's the basic state we call FL star. And as so now, if I think of the pockets, imagine again I have 4 of them, then the area, now there's 4 pockets and they're spin a half. So the area per pocket should be P over 8. All right, so this state, this very simple picture shows you what the anomaly argument also showed you, that if you have spin a half electron-like quasi-particles, then they will have area P over 8 per pocket. And furthermore, these green objects can tunnel from one layer to the other because they're just electrons. They don't carry gate charges. The spin-ons and the holons do. The spin-ons are still present. There's still a spin liquid state, but it has a Fermi surface with the wrong volume, with the wrong area. But these special particles, which are not anyons, the electrons, have no trouble going between layers. Okay. All right. So to summarize, I've talked about 3 possible states of a doped antiferromagnet. One which you don't lose the antiferromagnetism, where you get area P over 4. And this is seen when you actually have the antiferromagnetism present. The other is the hole-on metal, where again the area is somewhat unfortunately the same value, but of different quasi-particles that cannot go from one layer to the next. And finally here, the area is different, P over 8, but with quasi-particles with just ordinary electrons. Renormalized a bit because they're sitting on a bond rather than a site in the simple picture. And again, the main point is that everything about these pictures you shouldn't take seriously. I'm not saying cuprates look anything like this, but the area is very serious. It's because it's an invariant, topological invariant that cannot change. So this is a very useful way to compute what the area should be. Simplest way to do it. To show that it's really quantized is a bit more complicated, but all right, happy to discuss that later.
So
Yeah.
in a more realistic theory, so I have this sort of bound state with the quantum numbers as electron, but once its size gets to be somewhat significant, and
Yeah.
eventually you want it to tunnel, and there should be some sort of suppression of tunneling based on.
Yeah, so there will be some quasi-particle residue will be different as a function of momentum.
Right.
Yeah, so we put that into some of our recent calculations.
And is there a quantum type, not exactly that, but a suppression of the tunneling between?
There is, yeah. So there's more important is the momentum dependence of how it, for the things I'll talk about. And in fact, that is the subject of a recent paper by us. But you're anticipating what I will talk about in a minute. Yeah, but the overlapping is not a problem as far as the area of the Fermi surface. This is the simple picture. They can overlap as you want. The area of the Fermi surface will not change.
I didn't know you were heading for the MIT effect. I wouldn't worry again.
Okay, right. No, that's a good point. Yes, Samaya.
What about correlations? You expect the effect in masses to change?
Sure, everything will change except the area. And doing these computations is a difficult task, which I have struggled with for a long time, all of these other things, with many different methods. I'll show you the latest method due to Yaohui Zhang using ancillas, which I think is the best method. So you don't have to read all my old papers, but we are still looking for other methods to compute some of this stuff. I'd be very happy. I mean, there's still a challenge, but fortunately, as you'll see, the area is something you can measure. Yes.
So do I understand it correctly that the experimental signature of this general picture is that as soon as there is long range order, you should suppress the Kalea tunneling? Is that?
No. So this state does not have any order.
Yeah. That has Kalea tunneling, that state.
Yeah, but this one does not, and this also does not have any order.
But is that state ever observed?
Which ones?
The
whole method. Well, until the recent experiments, we didn't really know. So I'm coming to that.
Okay.
I mean, certainly this is a candidate, and I'm guilty of several papers where I was trying to make this compatible with the previous experiments.
Maybe I ask one more general theory question. So for FL star, I think the very low tech picture is I start with a spin liquid with a gap. I add a small number of fermions.
You don't need a gap, but go on.
But,
Yeah.
All right, whatever.
Yeah.
Okay. Well, but let me do a gap for a minute, just
Yeah.
it's easier in my head. But so then the state is stable to weak coupling between them.
Yeah, so in a condo lattice, that's correct. So for a condo lattice, this is relatively simple.
Yeah.
There's a low-tech argument, and you can show that the condo coupling does not destabilize the small Fermi surface.
So my question is, in that context, I'd be tempted to, if I think of the fixed point as essentially decoupled fermions and spin liquid, then most of the entanglement is, in your terms, bosonic entanglement is whatever, right?
Right.
Is that not true of this state, which is in
Uh,
some sense the spin liquid carries the boson?
Right, so I'm of two minds on that. If I really have a condo lattice where I can really think of the mobile electrons and the spins in different bands, then I would agree with you. But in fact, here we don't have that. So the difficulty, what I've struggled with a lot since our 2004 paper is how do you really construct such a state in a single band where there is no obvious separation between which electrons are localized and which are conducting. If you have a condo lattice, it's very natural to separate them. The F electrons are localized and the conduction electrons are not. Here I have to do it in a more democratic way. That is the heart of the problem.
Sure. No, in terms of technically, sure. I'm just wondering in terms of thinking of entanglement, but nevertheless, there's a sense in which.
Yeah, so let me show you some actual wave function with numbers that we have recently constructed. It seems a bit more complicated.
Before you come to that, I mean, so in this picture, higher energies, you cover the fractionalization in terms of the spin-ons and the holons.
The holons is a little delicate, yes, but the spin-ons absolutely have to be there. And so another prediction would be these spin-ons should be seen in high energy neutron scattering.
And what about the holons?
The holons tend to be overdamped, and when they condense their bosons, if you spin on the fermions, when they condense, they give you superconductivity. That's the last part of my talk if I get to it. But there are some indications, especially in experiments by Stephen Hayden on neutron scattering, of very broad continua at high energies, of the type that have been fit to spin on continua in other systems. And we have been trying, we have a recent paper trying to fit Stephen's data using some spin-on continuum. I haven't succeeded yet, I should say. It's a lot harder. But there is definitely a continuum. We can't compute it quantitatively yet.
Can I check whether I understood what you were saying about the spin liquid? I thought you said that you needed to have gapless excitations to fit with the Ishikawa argument.
I was very careful to say gapless excitation on a torus.
Oh.
Meaning that there are multiple ground states, for example.
Oh, okay. Yeah, all right.
Yes. All right. Okay. Let me somewhat shamelessly show you this paper in 2007, where this theory was at least in a figure caption. Okay, so now I want to talk about a recent experiment just published a few months ago. Of course, there's many thousands of experiments in pseudogap, and I show some of them in my previous talks, and everybody gets lost. So let me just focus on one because I think it's really the cleanest. I should say that there's a previous experiment by Brad Ramshaw and Louis Taillefer and others, which also saw some similar effects, but it's a little more difficult to interpret because they were looking at a different cuprate. So I won't say more about that other than to give them due credit. So the experiment I'll talk about is at Los Alamos by the group of Neil Harrison and Moon Chan. And in particular, they look at this particular material, the mercury compound. And here's the phase diagram. And they're going to be above TC at this red point, at a doping of 0.1. And they're going to apply at this red point a field of around 70 to 80 Tesla. Now, why is mercury just the ticket for the thing they're looking for? Well, mercury, I think, is the unique compound which has a very simple structure along the C-axis. So I do have to say a bit more now. It's not just square lattices. These are stacked square lattices. And in mercury, it has simple AA stacking. Okay, there's a copper on top of a copper, and the simple square lattices right on top of each other. And that makes the transport in the C-axis direction very simple. And that's really what enables. Many people have been looking at cuprates, but somehow mercury wasn't given the attention I feel it deserves. Like LSCO, which was looked at by the Brad Ramshaw's group, does not have that. The copper is in the center of the plaquette, so it has AB stacking. And that complicates things quite a bit. Okay, so what are they going to measure? They measure something called angle-dependent magnetoresistance. So what they do is they apply a magnetic field at an arbitrary angle theta with respect to the z-axis, and angle phi in plane. And they measure the resistance for current flowing in this direction, along the c-axis. So they get two-dimensional data for the resistance along the c-axis as a function of the angle of the field in all different directions. And so we want to understand that full set of data, which they did. I mean, I'm only showing you their results, by assuming that there are pockets of variable area. So the pockets have some simple quadratic dispersion. And then because of the very simple tunneling in this direction, the dispersion along this direction is just a cosine. So this is the dispersion they assume. And if you have this dispersion, this is what the Fermi surface looked like. It's like a very lightly warped cylinder. So these kind of Fermi surfaces are found in many other compounds, especially the organic materials, superconductors. And in those studies, as far back as '89, Yamaji made a very beautiful observation. So if I have applied magnetic field in this direction, semi-classically, the electron is moving in this orbit in the plane perpendicular to the field and right on the Fermi surface. Now, if they execute many different orbits and those interfere with each other, then you get Shubnikov-Tihas oscillations or Tihas-Van Alpha-Nofs oscillations and so on. And those are also seen in these materials at low temperatures down here. So, but the trouble is when you go to very low temperatures and see those oscillations, you also get a very large charge density wave, which completely changes the Fermi surface and again makes the interpretation very complicated. So they're not going to look at that. I mean, of course, it'd be great if you saw quantum oscillations at this high temperature, but no. So what they're going to observe is a baby version of quantum oscillation, which does not require interference of the electron with itself. It's essentially a classical effect having to do with the motion of the electrons on these orbits. So what Yamaji pointed out, that even classically, there's an interesting effect. There's a special angle that we now call the Yamaji angle, where the area of this orbit, it's a purely geometric calculation, is independent of where you put it to first order in the warping. You get the same area everywhere. And this means that, in fact, there's essentially no tunneling or no motion of the electron in the z direction. And so at that angle, the resistance in this direction will show a peak. And what Yamaji argued that just knowing that angle, you could, and knowing the spacing, the c-axis spacing, you could read off the Fermi surface, the area of the Fermi surface. So it doesn't require any further modeling, at least in this simple limit. Yes.
So what would be different if you were doing LSCO?
Because this is not true. This is not correct. The cosine, then you have other factors here that depend on kx and ky.
See.
Yeah.
So we're working at a temperature, what, about 90,
80 Kelvin.
80
Yeah.
Kelvin. And the field you said was about 80 Kelvin?
Well, so here's the actual data. You can see for yourself.
And P perp was,
Well, so yeah, I've forgotten what value they took. Anyway, so this is all of their calculations. So what they do is they take this dispersion. There's only a few fitting parameters. The area of these masses, the area of the chemical potential, and the value of T perp. And a scattering time. So they just take the classical Boltzmann equation. But you put in the Fermi function, and the dispersion is the dispersion I just showed you. So the quantum mechanics only really comes in this +1 and in this cosine. Everything else is classical. All right. So
How big is the resistive anisotropy?
I'm sorry, I don't know. It's quite large. Yeah, these are quasi-1 dimensions, quasi-2-dimensional materials. Okay. I mean, this warping is greatly exaggerated. And in fact, the Yamaji effect is strongest when the warping is very weak. If it becomes less anisotropic, there is no Yamaji. Because it's only to first order in T perp that the area is invariant. Great. Okay. So this is the data. This is the Yamaji peak. Here are different values of phi, which is the in-plane angle. This is the measurement, and these are their calculations from the very simple equations for the full theta phi dependence. And you can see it works very well. So as they say, the observation, these are their words in their abstract. The observation of Yamaji peak is evident for a small Fermi surface in the normal state of the pseudogap phase. It's really the best evidence yet of such a thing. Many people have talked about pockets in the pseudogap, and going back to Peter Johnson and photo emission, which was highly questioned in those days. But now I would say this is far more convincing. Yes.
This is delta rho C. This is not doing a theory of rho C at the same time.
This is delta rho between two different fields. Yeah, they subtract out the field dependence, I think, or angle dependence. Yeah, they said to emphasize the peak, they subtract high field minus some lower field. 70 Tesla minus 50 Tesla.
So my point being, if you were trying to do a single unified theory of the transport, you would also want to get the magnitude of rho C correct, right? Which is going to be.
Okay, but presumably, yes. Okay, this is the angle dependence. So that's not something that's angle dependent. Yeah.
Right, but it has a magnitude, which tells you other things.
Yeah, for the temperature dependence, right. I think they put in some temperature dependence tau here, but okay. But as far as the angle dependence, it's really the angle dependence. And we played with such models. It's highly constrained. I mean, I would turn it around. Okay, this is the theory. It's very simple. You have your favorite model, pseudogap. Come up with a theory to explain this. I'm skeptical anything else will work, but maybe you'll prove me wrong.
No, I don't mean that. I just mean if you have the theory, then tell me what rho C should be. But and I'm just this curve. This is not telling me what the actual rho C is, as opposed to just the change in it.
You mean you want to relate T perp to rho C? Well, that involves some. Yeah. Okay. I hasn't been done. Yeah.
And I guess this is also assuming that tau doesn't have any hotspots.
So it's
They
It's the
take,
same all
yes,
around the
yes,
focus.
but there is a, coming back to Shivali's earlier question, there is the T-perf actually does depend a little bit on where you are on the Fermi surface. That depends on the shape of this quasi-particle. And we did take that into account in a paper. I'll show you the reference to that in a minute. Let me make the punchline. And it doesn't change. I mean, we've done a better calculation than they've done. This is their calculation, and it doesn't change their conclusions very much. I mean, I think the fact that you don't have what's called a Lipschitz-Kosterlitz interference factor, which depends on the ratio of the cyclotron energy and the temperature. There's no interference. This can be just dominated by the region with larger C. It's good enough. Omega C tau is around 2 or something here. Yeah.
Yeah, so I guess my question is extremely related. So in the Ragdoll experiments on sort of neodymium LSTM,
Yes,
one
yeah.
needs a rather strong dependence of tau on K to get the magnitude resistance right.
Yeah, well, we've redone those calculations in that paper we're putting in the right. I mean, there was a paper on Loser et al. Also making the same point. And yeah, we've redone them now, and yeah, I think we can sort of understand what they're saying after putting on the K dependence of the quasi.
Well, but to be clear, here there's no K dependence of tau.
No, we haven't put that in. No. Okay. It's good to keep things simple. This is the simplest calculation that explained today. This is it. And you could just forget all this and take the Riemann angle and compute the area, and you'll get pretty much the right answer. Okay. All right, so this is excellent evidence for Hole pockets. And the whole thing has to do with going in some strange angle. So absolutely requires coherent tunneling from one layer to the next. Otherwise, you can't possibly explain this. And so that pretty much rules out the whole on metal, which was my favorite candidate for a while. Not anymore. It can't explain this data because you would have to have some very complicated incoherent tunneling between layers. As you see in the fractional quantum Hall effect, if you tunnel electrons in SDM in a fractional quantum Hall state, it doesn't show any quasi-particles. Okay. It also kind of rules out the spin density wave state or fluctuating spin density wave state. Because for a spin density wave state, and this relates to a question I believe, for the quasi-particles in the spin density wave state to tunnel coherently, you need the spins to be also coherent. You want the C-axis spin correlation length or the structure factor to have some Q dependence so that there are correlations between the spins, between the one layer and the next. And in this material, there's 0. The structure factor is Q independent, Q perp independent. And so it would mean that even if it was a fluctuating spin density state, it's hard to see how those electron-like quasi-particles can go from one layer to the other. Now you could say, okay, so well, you're putting 80 Tesla field. Once you put 80 Tesla field, maybe the spin density wave order reappears. Okay, possibly, maybe that's the answer. So I'm not going to rule it out. It's still a candidate. Okay, then what else? So then they say the small size of the pockets, each estimated to occupy only 1.3%, I'll come to that in a minute, is not expected given the absence of long-range broken translational symmetry. So the Hall coefficient here is positive, and P, so meaning that there's no charge density wave order, and there's neutron scattering that doesn't show, at least in zero field, any spin order. So anyway, they say it's non-expected. Well, okay, it was expected by us. And what about this 1.3%? Well, so if I take P over 8, the number I told you to remember, P is 0.1, P over 8 is 1.25%. Okay, so when I saw that, of course, I started jumping up and down. Actually, yes, somebody showed me about this paper in about 2 weeks. I didn't even read it. And then I said, okay, let me read it. Okay. And then I saw this P over 8 makes exactly what you should get. Whereas if I did have a spin density wave state, it would give you twice the area. We've also computed for the spin density wave state, assuming that's in this paper I meant to refer to. This paper has a more sophisticated calculation than in the experimental paper, including the anisotropic quasi-particle residue. And I'll show you how we determine that. What was I going to say? Yeah, so we have computed the theta and phi dependence for the spin density wave state, and it doesn't fit what they see, independently of this factor of 2. Okay, all right, so I don't think this is conclusive, but it's great to have in the cuprate field a quantitative prediction. If you know of another, let me know. I wouldn't say it's the conclusive evidence for spin liquids or long-range entanglement or fermionic long-range entanglement, but it's certainly the best evidence we have for pockets and a non-trivial quantum state. Okay. All right, so now let me turn to another set of experiments, which are done by cold atoms. Which, yes.
It's just historical side. I remember some discussion really did of ARPES of whether they were pockets or only half of Fermi arcs and so on. So
Yeah.
Is that still a confused issue? Maybe not.
So I mean, ARPES is more complicated, and we have papers on why the arcs are really part of a pocket. But certainly, I should say, Seamus is going to. Yes, Seamus did. I mentioned Seamus right down there. I mentioned this here, and also the YRZ theory, which also had. So, what Seamus saw the arcs. Where's that? Yeah. So, from STM and also for the mission, there's a. It's not really there, but we used to draw in a magnetic Brillouin zone. You see lots of intensity in some arcs over here. This is what they see. And certainly in the paper I'm referring to over there, and also by Jenny Hoffman, they said, okay, let's just close this off and compute this area. And this thing, where they just by hand closed it off, is in fact area P over A. Right, so that was just a proposal. Okay, this is, I would say, confirmation of that bold move.
But you have some story for why on Caesars.
Yes, we do. And for there, we have to take this theory and put in thermal fluctuation of the bosons that we were discussing earlier. And that's our, maybe I'll show 1 or 2 slides from that. Any other questions on this? Yes.
You mentioned that is this system going to have a charge density wave at low temperatures?
It does. Yeah, that's known.
So don't you expect some residual order to exist at high temperature as well?
Well, so what's known is that when you have a charge density wave and you see quantum oscillation, the Hall coefficient is negative. So that's where you get the Sebastian Harrison electron pocket, I believe. Okay, and that's due to the charge density wave. So if you look at this material here, where did I go? I did not go back. Yeah. So if you measure down here, which has been measured, you see a charge density wave, and you see a negative Hall coefficient with long range charge density wave order, and you see quantum oscillation. But over here, the Hall coefficient is positive. So I would say that's evidence that even if there's fluctuating charge density wave order, it is not doing much to the Fermi zone. So really, this is at least in terms of transport, is the first evidence for a Fermi pocket in a regime where the Hall coefficient is positive. All the other evidence for pockets from quantum oscillations in a regime with the Hall coefficient is negative. And I believe that's due to the presence of charge density there.
So only a system with more than one type of pockets will explain this evolution. If you have hole and electrons.
Well, I mean, there's a broken symmetry. I can give a whole other talk on how we have how that transition happens. That requires. So here I'm just talking about the simplest thing. I'm talking about, that's what I think beautiful about this experiment, looking at the underlying parent state of the superreactor. There's an incredible complexity as you lower the temperature with superconductivity, phase fluctuations, charge density waves, and all of that is correct. But those, I believe, are secondary effects to this underlying quantum state. So, all right. So now I want to discuss some evidence from cold atom experiments of a similar picture. Okay. So what you can measure in cold atoms is like very different. They can't measure Fermi surface. I should say there's thousands of numerical papers on the doped Hubbard model. Not one has seen FL star. But yet I didn't lose faith. or any fancy quantum computer. And the point is that none of those experiments have the resolution to see a pocket at 1% of the Brillouin zone. It's just impossible. So this is really an amazing experiment. It's highly sensitive to some very fine momentum space structure, which no numerical study has ever seen. But hopefully I've shown you some very general arguments that such a thing should happen. Okay. All right, so now cold atoms, however, they also can't see Fermi surfaces. They don't have systems big enough to see 1% of the Brillouin zone, but they do have a different advantage. They can measure locally highly complicated correlation, multi-point correlation function. They can see every electron or every fermion, in this case, the atoms. They can see every fermion and measure both its spin and charge by a single snapshot, and then take millions of snapshots and compute things. So unlike the Fermi surface area, which I can just wave my hand and tell you what the answer should be, for this, you need an actual wave function. You need more information about the state. And this is what we've been struggling with for a long time. And I'll tell you about our latest attempt to how to write down actually a wave function for FL star in a single band model, in a Hubbard model. It's not a problem to write it in a Kondo lattice model, but it's not so easy to do it in a single band model. So this is some of the experimental data. So they're working up here, and this is their fanciful phase diagram, but their measurements are up here at this relatively high temperature. And as they cross from here to here as doping in an optical lattice, they measure the local three-point correlation function. Actually, there's a new paper where they also measure 5-point correlation function on much bigger systems. And yes, I'd love to be able to model that, but we're not there yet. So what they see is that they look at every atom and its spin, and then some fraction of the atom's sites are empty. So you translate that to be into the center. And then around that empty site, you measure 2-point spin correlation functions by just taking many, many, many shots. So they're measuring equal time, 3-point correlator, 1 hole and 2 spins. Yes.
This is the fermionic.
Yes, absolutely.
Okay, so the term polaronic, which just appeared, means what?
In fact, that's their term for FL star. Polaronic means it's a polaron, which is a bound state of a holon and a spin-on. I wouldn't have used the word polaronic, but that's what Eugene Demler, they have string picture and so on. Their arguments really rely on the presence of long-range antiferromagnetic order. And Eugene has often said that, oh, that doesn't matter. Hopefully I've shown you, with this, when you think about the Fermi surface area, it does matter. Anyway, so the polaronic string picture is very much in the spirit of FL star. So they, of course, I would love it if they call it FL star, but anyway, they call it polaronic. That's fun. So what I want to emphasize here is that these correlation functions, we won't go into the details, really evolve a lot. These are short distance correlations at a relatively high temperature where there's no broken symmetry whatsoever in anybody's theory or any condensed matter experiment. Yet the local structure of the wave function of the atoms, in this case, fermionic atoms, changes dramatically. So this is already at the face of it, some evidence that there's something much more underlying quantum about the difference between the Fermi liquid and the polaron, and the pseudo gap, and not some precursor to broken symmetry. Okay.
Can I just ask?
Yes.
The 3-point function, so it's something like 1 minus n s dot s or something.
Correct. Yeah, you put the n at the center and the s all those different points. Yeah, so there are lots of tensor network calculations now of these kind of things, which are almost as good as the experiments. And yeah. All right, so I'll tell you about our calculation. So now I'm going to try to construct a wave function for the FL star state at finite density, which no one has written down before. And this is really based on a brilliant idea by Yaohui Zhang, who's now on faculty at Johns Hopkins. So this is the physical system, holes of density 1 plus p that I want to understand. And I'm going to add a bilayer of ancillas, okay? So these are things I'm going to, as a theorist, just use. And I'm going to use them to construct a wave function in the physical system. You know, just like in quantum, all these quantum computers, sometimes you have ancillas, and the ancilla's main use is to you can measure them or do something, and that entangles the things you're actually interested in. So that's pretty much what we're going to do. But it's very important that I take a bilayer, not a single layer, because only with a bilayer is trivial as far as the Oshikawa anomaly is concerned. So if I had a bilayer, and imagine there's some coupling J perp, they can just form a vegetable, just singlets with a gap, which is completely invisible at low energies. So in fact, that is what you want to do in the Fermi liquid regime. Just have essentially free fermions. And this is just, for now, there's something sitting around. And in fact, there's something called a vanilla wave function that famous people work with, which is essentially a free fermion with a large Fermi surface with some additional Gutzwiller projection, which you can put in if you want. But they in particular argue that this vanilla holds all the way, Phil Anderson in particular, all the way down to the pseudo gap, which I totally disagree with. This is not the correct wave function in FL star. And it will totally disagree with the Collider experiment explicitly. You compute these things, they won't look anything like the Collider experiment. Okay. So I'm going to construct, using these ancillas, the FL star wave function. So what we learned from the anomaly argument that this wave function should have two components. It should have a Fermi surface, and it should have a spin liquid. And the advantage of ancillas is I can separate them at least to begin with.
Just to be clear, we have 3 planes now?
Yes, 3 planes, thank you. You can't add 2 planes because, which many people have done. That's incorrect because that's a half-fill system with a non-trivial ground state, and a non-trivial anomaly changes the physics. You can add 2 though. You can add any even number. 2 is the simplest. Okay, all right. Yeah. Okay, so now I want to use these ancillas in a more non-trivial way rather than just putting them in a gap trivial state to get a wave function for the left-hand side. So what I'm going to do is, I told you I need both a Fermi surface, which is small, and a spin liquid. And that's kind of the use of the ancilla approach. You don't have to read Oshikawa's paper. It's like Oshikawa for dummies. You do things carefully, you'll be sure to satisfy Oshikawa. So I'm going to put a spin liquid in the bottom layer, anything you want, but in fact, for other reasons, you have to put a gapless spin liquid, but it's not crucial for now. All right, so there's my spin liquid that's present in FL star. And then how am I going to, where I've written these S2 spins in terms of some spin-ons F. Okay. And a simple wave function for that spin liquid is just a Slater determinant with some Gutzwiller projection that many, many people have worked on. And in recent years, in fact, those types of wave function actually do very well in explaining a lot of numerical data on the triangular and Kagome lattices. Okay, and then I have these top 2 layers left. And what I'm going to do there is just take free fermions on the top 2 layers. So I will take these spins and write them in terms of fermions F1. And then just as in a Kondo lattice, I'll form a Fermi liquid state. So what we know from thousands of experiments on heavy fermion compounds, if you have conduction electrons and spins, when they form the Fermi liquid state, they form what's called a large Fermi surface, which counts in its area both the electrons and the spins. That is the state that's seen in the vast majority of heavy fermion compounds. So I'm going to do exactly that. So in some sense, what I'm doing with this thing is I'm taking two well understood states. I'm taking an insulating spin liquid, and I'm taking a Kondo lattice Fermi liquid. Now, in this case, what is the area of the Fermi surface? Well, the density of holes here is 1 plus p. The density of holes here is 1. So the total density of holes is 2 plus p. Now remember, in the Luttinger argument, you can always remove 2 because that's a filled band. So everything is modulo 2 in the density or modulo 1 in the area. So in fact, this gives me my small pockets. So I've constructed, at least for this 3-band model, both the small pockets and the spin liquid. So that's okay, starting to look good. But it's a wave function for a 3-band model. It's not what I want. I want a wave function for a single-band model. Well, what I'm going to do now is I'm going to do a projection or a measurement. I'm going to measure this, a bell pair, as it's called, I guess, project onto a singlet, the spins S1 and S2. So these will now disappear from my wave function. And the only dynamical degree of freedom will be the electrons themselves. So this is now a wave function just for the Hubbard model. And as Yahweh likes to say, you can think of this as, first of all, you have a Fermi surface. And then by this bell pair measurement, you teleport the entanglement of the spin liquid into the fermions. This is the non-trivial step, which we can only do numerically. And this is why I was saying, okay, it's more complicated here. You have to do this kind of bell pair measurement to finally get the state you want.
You only check that the topological degeneracy that you built in does get.
Well, so you can do this at the level of gauge theories. So what happened, the short answer is for the same reason. So in this phase, there's various gauge fields you have to put in, which I won't go into. But there's a gauge field here, which is associated with the spin S1, which is actually Higgsed in this large Fermi surface phase.
You did numerics.
No, we don't do it. So numerics we've done. I'll show you the results in a minute.
Yeah, but in the numeric, can you check that the orthogonality of the ground states on the torus, let's say from the bottom?
We certainly haven't done that. That's hard. But at the level of, so what we've understood from studies of Kondo lattices or other systems, that when you do a good Sula projection, or hopefully that you can think of as an integral over some gauge field. But if that gauge field is already Higgsed in the phase you're studying, you don't expect that to have such a strong effect. So that's our argument, that this projection operation does not change the Fermi surface area. It could change everything else, but it won't change the Fermi surface area. It has to do with the Higgsing of certain gauge fields. All right. So in fact, here there's this, good. There is a Higgs field actually, just the hybridization, the mixing between the top 2 layers, as people in the Kondo lattice field know. This is the slave boson of Pierce-Coleman and others. Is the analog of that. And so as long as there is a mixing, and then you're in the small Fermi surface state. And when it's unhiggsed, that's when you go back to the Fermi liquid. The projection just gets rid of this part, and you're just back to the old Fermi liquid. So there's a phase transition between FL star and FL. It does not involve symmetry breaking, but it does have a kind of like a gauge-dependent autoparameter, or Higgs field as its autoparameter. And that's what we use to answer all the difficult questions Shivaji was answering, is to work with that gauge field, but I'm sparing you those details. All right.
But at the very high level, the filler projection of Fermi seas is a way to construct minimal spin liquids. This is fancier with filler projection.
Yeah.
With the spin liquid added in as a factor.
Yeah, so we have a lot of experience in showing that good filler projection or other projections don't change the number of Dirac points or the size of the function. And we can use very similar arguments to argue, I haven't proven, that this bell pair measurement does not change the size of the Fermi surface. Okay, so no, this is calculation. Actually, the data here is due to Lehner-Shackleton. So this projection operation is very tricky. In fact, in the methods that were implemented in this paper, there is a sign problem. So we would love other trial wave functions and other methods of evaluating this projection that don't have a sign problem. That would be really, really useful. But in the limited systems we were able to study, we measured we had a variational parameter, a single variational parameter, which is just this Higgs value phi, and it goes to 0 as a function of density at some point. So here you have an FL star and there you have an FL. That's determined numerically, the value of phi. And these are the comparison between the measurements of various local correlations around a hole and our Monte Carlo calculation. Well, I'm not author of this paper. The data is by Shackleton, my former student, and Xu Zhang.
I think just to connect your old heavy fermion work, the FL star and FL, the Higgs thing is reversed for that, right? Because there the heavy Fermi surface has phi not.
Excellent observation.
Yeah.
I have whole papers on that point, but yes, that's also a very curious thing here. And that means, for example, in our recent paper, we've said that the thermal power, which is sensitive to particle asymmetry, in fact, this Higgs field is particle asymmetric, will be inverted between cuprates and heavy fermions. And in our paper, we also make some argument that at least there's data to support that idea. How am I doing on time? Okay, so then the rest of my talk I'm going to skip. Yes, okay. Yeah, okay. Basically, so this is the SYK model. It gives you this is the Yukawa SYK model with the boson coupled to fermions. That appeared in various papers, but especially this beautiful paper by Estelis and Shmalian in this form, which has very similar properties. So this is a zero-dimensional model, but this phi is suggestively named. We're going to promote everything to 2 dimensions, put a Fermi surface here, put in some spatial randomness, and get a theory of the strange matter. So that's what we've been doing over the years, trying to understand this transition. So let me just jump ahead to the very end. What's happening? Okay, slow, or because I'm sharing the screen. Yeah, so there's a lot to say, but I'm happy to discuss this further. Yeah, I've mentioned this kind of. So one very important thing is now, a main point I also want to make. I have very different normal states with presumably a quantum phase transition at 0 temperature if they existed down to 0 temperature, but they don't in any experiment. They're preempted by a superconductor. So an important constraint on the theory is that the superconductor have no phase transition, since none has been observed. It's just a vanilla BCS superconductor, but nevertheless, the phase transition between these 2 states is very different. This is a confinement transition in the gauge theory, and this is just the usual BCS transition. So even though the state is BCS, the underlying physics of the transition is very different at different dopings. And using this thing, we can get, these pictures of vortex cores that Seamus has measured. Yeah, so this is the summary slide. So these are the 3 metallic phases I've talked about. Certainly, this has been observed without any doubt with antiferromagnetic long-range order with the pocket areas P over 4. This has also been observed without any doubt. And okay, there's starting to be increasing evidence, shall I say, that this is the relevant metallic state in this pseudo-gap regime. So this is a state with many fermion entanglement. And even for the transition, we have a different type of state based on these SYK physics without symmetry breaking for the strange metal. And let me end by showing some of my collaborators. My former student, Maine Christos, who's now at Caltech. Pietro Bonetti, a postdoc, was just started as a group leader at Max Planck in Stuttgart. Alex Nikolenko, graduate student who will be eventually looking for a job. And Avishka Patel, now former student, postdoc, faculty in Bangalore. And the part I didn't show you, there's a Monte Carlo study for some of the questions that Shivaji mentioned with a group in Chennai or Madras. Thank you.
Thank you very much for the nice talk. We had plenty of questions during the talk, but let me take just 3 more questions if there are pressing questions. Okay, Amalia.
How this problem can be expanded also to other family of superconductors?
Well, probably not. I think the pseudo gap as a phase without any broken symmetry is rather unique to the whole doped cuprates. For the electron doped cuprates, I'd be mostly comfortable, although there might be some tiny region where this doesn't work, of just taking a phase diagram where this disappears, it basically shrinks to nothing. And for the pnictides, certainly that's the case. So this intermediate metallic phase seems to be rather special to the whole doped cuprates, I would say. Yeah, it'd be nice to find other materials. If you take a spin liquid and you dope it, I think you will find such a phase, but okay, maybe you can do that now. Yeah, so, and also the whole doped cuprates are the materials with the highest DC. So it's very tempting to say there's a connection. I believe there is, but I certainly haven't proven it.
Yes, if you have a spin-on, you have 3D9, it has a yarn-teller distortion in copper. If you have a hole, you don't. So when you have an entangled spin and hole, what happens to the yarn-teller distortion, and is that significant for the way these composite objects pop around?
Well, so there certainly are phonons around we associate with such a distortion. They're at relatively high energy. What I would say is that if you look at higher doping P, where you have a Fermi liquid and where the photo emission, you always see just a single band crossing the formula, okay, independently of how it was built out of copper, oxygen orbitals, and phonons, and so on. There is a slight kink in the dispersion, which maybe is connected to some C-axis phonon, but it's not believed to be an important effect. Okay, so here the assumption is that experimentally, independent, of course, the one band Hubbard model is an approximation, and I'm not going to say I don't have anything tied to it. And some people like to work with 3-band models with phonons and so on, no doubt. And certainly for some of the numbers that could well be important. But the only thing I'm using here is that photon emission has never shown anything other than a single band crossing the formula. And that's really all I need for most of the things I've talked about.
Ruby? So if I've understood correctly, the Yoshikawa argument doesn't kind of make some rule with the anomalies.
Yes, yeah.
Which, like, what's possible gives certain contribution and stuff.
At least for the anomaly, you can just add it up.
Yeah.
Once you start talking about the wave function, it's much more complicated.
Sure.
Yes.
So how does that work for the strange metal phase? I guess like it isn't going to have any problem.
Yeah, so the string, well, no. So at least in a clean system, if you have a non-Fermi liquid, so a non-Fermi liquid has actually a sharp Fermi surface. It's sharp in momentum space, but not sharp in energy space. So the spectral function is broad as a function of frequency, but there is definitely a very well-defined Fermi wave vector. And so in this case, in fact, we take a large Fermi surface. In non-Fermi liquids without disorder, there is a sharp Fermi surface, and the area enclosed is the latticular. Yeah, so that's another important point that, when people talk about non-Fermi liquids, I don't like that word very much because even a non-Fermi liquid has a Fermi surface. Just like, the HLR state in the quantum Hall, it has a Fermi surface, which is precisely defined and can be measured. And it does obey the latticular in the experiments and even up here.
Okay, with that, let's thank Subir one more time.